OK, so when we did HQET, the first thing that we did is we started to expand. Before we designed the effective Lagrangian, we just said, well, what happens if I expand the full theory? And I'm going to take the same attitude here. Let's just write down some full theory objects and expand them in the limits that we've been talking about. And then we'll see what kind of effective theory we want based on the results from those expansions. So let's start with spinors in a linear limit. So let me start with some massless QCD spinors in the Dirac representation. We could use some other representation, but let's just use Dirac. So we have spinors for the quarks. We have spinors for the antiquarks. V. Where this curly V and this curly U are two-component objects. Make sure it looks curly enough. So what we can do here is we can expand, and you see that what happens when you expand is that you can think about the P3 vector being larger than P1 and P2. So let's just let our n be 1, 0, 0, 1, and an n bar be 1, 0, 0, minus 1, so they're back to back with each other. And we just expand. Whether I put the plus or minus 1 there or there doesn't really matter. Let's expand in n bar.p, which in this case is P0 plus P3 being much greater than P perp, which is P1 and P2. And then that's much greater than n.p, which is P0 minus P3. And what that means is that you can approximate sigma.p over P0 for these massless particles is just sigma 3. Because you pick out the P3, that's the big component. The P1 and P2 you can drop. Then it picks out the sigma 3, and then P3 is also the same size as P0, so you're just getting sigma 3. So what you get from this then would be guys that look like this, which if I put in the two possibilities for the curly U are 4-component spinors that look like this for U. And then likewise for V of P. We can work out what we get. We get that. So this is actually a little different than HQET. In HQET, what you would have found is that the antiquarks would have been just left out, and the quarks would have been there in the theory. Here, both of them survive, and actually 2 degrees of freedom survive for both the particles and the antiparticles. So it's not like we're integrating out something like the antiparticle, like in HQET. By this expansion, we still have all 4 of these degrees of freedom, if you count degrees of freedom by whether you have particles, antiparticles, and spin states. Nevertheless, there is a simplification that occurs, and that is the fact that the spinors that you have a projection relation. So if you look in this basis that we're talking about here, what n slash is, if you write down what the gamma matrices are in the Dirac representation, then n slash is this. And another useful thing is n slash n bar slash over 4, which you can work out. It's just this. And these spinors here, which I need a name for, so let's call this un and call this vn. They satisfy n slash un is n slash vn is 0. And they also satisfy n slash n bar slash un is un for both of them. So what we can do with that is the following. We can take the identity in this 4x4 space, and we can actually write it as n slash n bar slash over 4 plus n bar slash n slash over 4. And that's because, remember, that gamma nu is 2 g mu nu, and n dot n bar is 2. So this is just one way of using those. This is the anti-commutator dotted into n and n bar, so I can write it out that way. And this kind of formula here is a formula that is for projection operators, right? So as you act with the operator and you get the guy back again, so you could act twice with that operator. And so what you can do with this one is you could let one act on psi of QCD. And if you did that, you'd get n slash n bar slash over 4 psi plus n bar slash n slash over 4 psi. And you could define these two pieces as being two different components of the full theory field that I'll call Cn and psi n. And what happens at high energies, because of the type of thing we were doing over there, is that we only like to produce Cn's. We don't like to produce psi n bars. So if you look at some high energy process, this sort of thing I was doing with the spinors basically boils down to one sentence. And that is that we produce or annihilate the components, the guys that live in this Cn. Not the so-called small components, which live in this other guy. This language of calling them the small components is something that goes back to the early days of QCD, actually. But we may say that word a few times, but the history won't be so important to us. OK, so much for the spinors. There is some simplification in the spinors, because we do like to produce certain combinations. But it didn't really teach us about something that it didn't really teach us too much beyond that. And we didn't see that we lost a degree of freedom like we did in HQET. But nevertheless, there was some simplification.